Good evening, everyone. My name is Denise Melchor. I'm a grad student at UCLA in the astrophysics program, and today we'll be hearing talks from Professor Smadar Naus and grad student Rory Bentley, both also from UCLA. We'll first get started with Smadar's talk on gravitational waves, and then we'll move on to Rory's. And after both talks, we'll have about 5 minutes of questions for each presenter. And then at the end, stay for our trivia, which is about 10 minutes. We'll go through each question for 30 seconds, and then we'll go through every question once more. So make sure to stay, and then we'll go through the rules again. And so if we'll give it one more minute, then we'll allow Smadar to begin. Oh, it's 7:01. I'm going to stop sharing soon, and then Smadar will be able to present. First off, I'd like to introduce Smadar a little bit. Professor Smadar Naus received her bachelor's in physics in 2002 from the Hebrew University of Jerusalem and her PhD in physics in 2010 from Tel Aviv University. She was then a Gruber Fellow at Northwestern University and an Einstein Fellow at Harvard University before joining UCLA faculty in 2014. She has been awarded many fellowships and prizes such as the Cannon and the Warner Prizes, awarded by the American Astronomical Society. Really excited to hear Smadar's talk on gravitational waves because it's one of my favorite topics, and she's also my research advisor. So I'll stop sharing, and then Smadar, you can go ahead.
Thank you, Denise, for that very lovely introduction. I'll share my screen. All right. Hi, everyone. My talk, my research in general covers many topics, from studying the formations of the very early galaxies all the way to the mysteries of black holes and stars and even planets. And there's one thing that connects them all. It's physics, and specifically gravity at different scales. And this is what I think that astrophysics is all about. We're solving physics problems at different astrophysical settings. And in this talk, I'm going to focus on one astrophysical setting, which is the heart of galaxies. And I'm going to show you that these are natural places to find gravitational wave sources. But in order to understand what's so unique about the heart of galaxies and what are gravitational wave sources, we need to travel back in time about a billion years ago, because this is where our story begins. It begins when two distant black holes spiraled together and collided, and we say that they merged to form one single black hole. Now, these two black holes, they were about 30 times the mass of our sun. And when they merged and became one black hole, for a brief moment in time, they shone so brightly that they overshone all the stars in the universe combined. But they did not release this energy as light, but instead they released this energy as gravitational waves. So gravitational waves are little ripples in space-time continuum that take place when two masses accelerate toward one another, just like in this little video, or just because it's very similar. If I'll put my hand and I'll in a pond or in a bath, and I'll accelerate, I'll move it fast. But the thing is that space-time is really stiff. It really doesn't like when things try to perturb it. So even though for that little moment in time, those two black holes billion years ago released all their energy, all the energy that they released overshone all the stars in the universe, the amplitude of these waves were so small, so tiny, that it was 1 part of 10 to the power of 21. So this is 1 with 21 zeros behind it, which, if you think about it, is really, really tiny. But nonetheless, in about 6 years ago, it was detected with LIGO. LIGO is called the Laser Interferometer Gravitational Wave Observatory, was able to detect those very tiny little ripples because it has these arms. You can see here one arm, and then there is another arm here. And these arms is about 4 kilometers. And these gravitational waves, when they propagate and they reached us, so it took about a billion years for those waves to reach all the way to us, they stretched and squeezed those arms just a tiny bit, in 1 part of 10 to the power of 21. And LIGO detected them. LIGO has 2 sites in the US, one in Hartford, Washington, and one in Livingston, Louisiana. And there is another observatory in Italy called Virgo. And since then, LIGO Virgo Observatory and collaborations were able to detect many, many black holes. And that detection 6 years ago, the first detection and those that followed, forever changed the way that we sense our universe. Because before that, we relied on light or any electromagnetic radio, X-ray, any electromagnetic radiation. But now we can sense our universe with something other than that. And that yielded the 2017 Nobel Prize in Physics. So what did LIGO observe? So here I'm showing an illustration of what LIGO observed. The x-axis here, the horizontal axis, is arbitrary, and the vertical axis are masses in solar mass, so how many times the mass of our sun. And we can see many things, that there's a lot of things going on in this little illustration, but I want to draw your attention to all those blue dots. All those blue dots are basically black hole pairs that merge together to become one black hole. We call black hole pairs, black hole binaries as well. And in fact, LIGO estimates that every 15 minutes in our local universe, 2 black holes find each other and merge. So during the time of Astronomy on Tap, there'll be about 4 in our local universe of black holes that will merge. That is pretty amazing. It's even more amazing when you think about what was the expectation prior to LIGO's detection. Before LIGO made their detections, people that work on this topic expected that LIGO will not see black hole mergers, that in fact, black holes don't tend to merge with other black holes so often in our universe. So what I want to do now is I want to walk you through of some of the challenges of these black holes to merge together with another black hole. So I'm going to describe a recipe. We have our chef here, and we want to understand how black hole merge. And the first thing to think about is that these black holes that are about 30 solar mass of our, 30 times the mass of our sun, we think that they are the end result of a very massive star. So if we have a very massive star, and this star needs to be more massive, between 20 to 100 times the mass of our sun, and as it grows and evolves, and it starts to finish up its hydrogen supply, it goes through a midlife crisis, and it expands a little bit in the center. And after it expands and also loses a little bit of mass, it ends its life with a big explosion called supernova and leaves behind a black hole. Black holes are very simple creatures in nature, if we think about this. These are creatures that nothing can escape them, not even light. This is why we call them black holes. And they are defined by 3 simple parameters: their mass, how fast they spin and rotate, and if they are charged, how much they charge. But this is a bad pun, I know. I like to tell jokes. It's always very hard to tell jokes on Zoom because you don't know if your jokes are even funny. And I know that my jokes are not very funny, so I'll just assume that you just smiled for courtesy. Anyways, so we want to have 2 black holes. So that means that we need to start with 2 stars. So maybe the first question to ask ourselves, whether or not 2 stars are common in our universe. So the answer is yes. Well, this is a picture, of course, of Tatooine. I'm a big nerd. You can see from my background, this is My background is Star Trek. This is Star Wars, two different stars, but yeah. But not just in Tatooine and in the movies, two stars are common, but also in our universe. So two stars being born in binary stars are really common. In fact, our sun had a 50-50 chance to have a stellar companion. And we can think later if it's a good thing or a bad thing that we don't have a stellar companion. So we have these two stars. Now let's them evolve. So here is one star going through its midlife crisis. But what happened here is that I drew these two stars too close to one another. And they start, in fact, to eat each other. And this mutual eating phase, we see it in our local neighborhood quite often. So this is this is a better artist impression than my two stars here, but this is what we see that happens. And we know that at the end of the day, these two stars will eat each other to become one star. And then at the end, one black hole. That's not good because I wanted two black holes, not one black hole. I want to end up with two black holes so they can merge with one another. So then the answer may be simple. I just need to draw them further apart. And then each of them will evolve by itself, go through supernova, and become black holes. So here I'm left with two black holes. However, calculations that were made prior to LIGO's discovery found that in order to overcome this stage of eating each other as a star, the two stars eating each other, will result with the merger time to be larger than the age of the universe. That means that we cannot, in a simple way, merge these two black holes. So we need to help them somehow. Now, there are all kinds of interesting ideas in the literature of how to help two black holes to merge. And I'm going to tell you only one part of the story, which is how the unique place of the center of galaxies help out. So for that, let's travel to the galactic center or some galactic center. And we know that in the center of almost every galaxy, there are supermassive black holes. These are extreme mass black holes with masses between millions and billions solar mass. So these are really different type of black holes than the one that I just talked that merged. These are huge ones. And we know that not only do we have these huge monsters in the heart of galaxies, but that surrounding these black holes are dense environments of stars and stellar remnants like smaller black holes and also other stuff like white dwarfs, neutron stars. And in fact, when we have this type of systems, then not only they feel the enormous gravitational pull from the supermassive black hole, but they also feel the gravitational pull from one another. Luckily for us, we have a supermassive black hole at the center of our own galaxy. We have our own monster, and very detailed observations of that place found that our supermassive black hole mass is about 4 million solar mass, the mass of our sun. And I really want to highlight that this discovery yielded the very recent the Nobel Prize of 2020 from last year. And I also want to highlight Andrea Ghez, colleague and a friend from UCLA. And we're extremely proud of her and her success, a well-deserved prize. And we're still in celebration mode. We haven't finished celebrating. And detailed observations, the one this unique place may host a lot of pair of stars. And therefore, if there are lots of pair of stars together, then maybe there are also lots of pair of littler black holes. Now, all these observations of our own center our own galactic center means that whatever properties and behaviors that we find in our galactic center probably applicable in other centers of galaxies, because our galaxy has nothing special about it. And I know it sounds so harsh to say that on our own galaxy, but it's really just a regular galaxy. So that's really good because we can use what we learn from our own galaxy in other galaxies. And Rory will tell you more about this as well, I think. So let's think a little bit about the environment around a supermassive black hole in our own galaxy. So here is an image of it, and I want to compare it to our own neighborhood around our sun. So the closest star to our sun, called Proxima Centauri, and it's about 4 light years away from us. And between us and our closest neighbor, there is nothing. There are no other stars. This is just the closest neighbor. And if we will look around the supermassive black hole with a similar volume, we will find that there are about a million stars there. So thinking again about 4 light years away from the supermassive black hole, same volume of space, but there are a million stars compared between us and Proxima Centauri, nothing. Just imagine how the night sky would look if we had a million stars between us and Proxima Centauri. So what does it mean? It means that it's really hard to live as a pair of anything, pair of stars or pair of black holes around the supermassive black hole. So here is a pair of objects, 2 black holes, for example, littler black holes. This is not to scale. These are the 2 little ones around the very, very big one. And they encounter constantly a lot of different neighbors. And as time goes by, these neighbors just a little bit and a little bit interrupt and tug gravitationally on this pair until they unbound it and they break up the binary. That's not good. That means that it's really hard to merge them. That seems like I'm telling you a story how it's impossible to find gravitational waves near a supermassive black hole. But as was shown also by my group, is that this process takes time. So if we can actually merge the system before that, maybe it can be very efficient. So another thing that we want to think about is how the supermassive black hole affect this binary before it's broken up, before the pair is broken up and no longer a pair because of interactions with other things around it. So here is this system, and what this supermassive black hole does, it perturbs, it changes and alters the orbit of the 2 little binary as a function of time, the 2 little black holes or the 2 stars as a function of time. And what it actually does to it, it makes the orbit more and more elliptical. And in fact, it becomes so elliptical that it finally merges. That's a bad animation, but it gives the point. So in fact, as time goes by, we find that black holes, littler black holes, can merge before any interactions with the neighbors, thanks to a socially distant supermassive black hole, extremely big friend. But I also told you the story how we actually want to follow the stars that evolves, and that's not a problem at all. We can look at stars as they begin their lives near the galactic, in the galactic center, near a supermassive black hole, and we can follow them from being babies all the way to old age, even death. And they form all kind of interesting pairs, from black hole pairs and other types of pairs like neutron stars or white dwarfs or neutron stars, black hole. And in my group, we studied this and we showed that this process is very efficient to form many, many gravitational wave sources at the center of galaxies, just like our own. Now, something that I kind of hinted at the beginning was that, well, there are all kinds of ideas in the literature. A lot of people are working on this problem, how to merge 2 black holes, giving the challenges that I told you at the beginning of my talk. In fact, I think that theoreticians such as myself are really good at coming up with all kinds of ideas. But what we really need to do is to know how to disentangle between the different ideas that we have as scientists. And that means that we need to come up with all kinds of ways where observations such as LIGO and what LIGO observed will be able to disentangle between the different ideas. What might bring able that will be different than other people's. And in addition, we can add other observatories, upcoming observatories, such as LISA. So for example, LISA is going to be a much larger arm. So LIGO arms are about 4 kilometers, 2.5-ish miles. And LISA is going to be along the millions of kilometers. And it's going to be in space, and it's going to be able to observe these pairs way before they're going to merge. And then we can also try to combine this with Hubble and maybe even James Webb that will be launched very soon, and also some ground-based observations. And together as a community, we're working to try to understand these really interesting observations done by LIGO and the upcoming ones. Now, really in the last minute, I mentioned my group a lot, and I really want to, I'm so proud of my group. And you've seen Denise in the beginning, so here she is here. But I work with a lot of students and a lot of people, and I unfortunately could not talk about everything that each of them has done. But here also I want to say that they're all here in their very, I would say, professional pictures. But during Zoom, which was all of last year, we were all having fun over Zoom. So just to sum up, what I showed you is that the heart of galaxies are excellent places to find gravitational wave sources. And I'll be more than happy to answer any questions that might come up.
Thank you, Smadar. So there's a question in the chat for you. I'll read it to you if you'd like. Why is it important for the stars to become black holes instead of merging and exploding?
Oh, that's a very good question. In fact, we are also thinking a lot about two stars that merge with one another and how that will look. This is actually extremely exciting, because there are some observations that suggest that there are this star merger remnant that are just going about their business in the galactic center. So it's actually very cool to have two stars that merge. However, if I do want to merge two black holes, I need to keep having two black holes. If I have two stars that merged and then became one black hole, it's hard to find another, the likelihood that it will meet another black hole in somewhere, it's not zero, but it's extremely small. To understand why black holes often meet each other and merge, which is about every 15 minutes, I need to be able to do it very efficiently. And then there is another question. It says, is everything in the center of galaxy going to fall into the supermassive black hole? That's a very good question. So supermassive black holes are not really a vacuum cleaner that are going around and eating everything. They are there, and if something is wandering about and getting too close, then it will fall in and then will be eaten by the supermassive black hole. But the system outside is more or less stable. And I'm saying more or less stable because there are actually a lot of other type of collective dynamics that is also including the supermassive black hole in the center, but also include the fact that we are at the center of a huge thing as a galaxy, and that there are a lot of stars and stellar remnant that's slowly flowing in. So it's not that everything is really will be sucked in to the black hole. but some things that are slightly heavier than the regular stars will find their way in. It's called mass segregation. And that's actually similar if you'll have a bag of rice and you'll put in the rice some things heavier, let's say some marbles, right? And if you'll shake the rice enough, the marbles will find their way inside the rice. Yeah. And if there are no more questions, I'll be happy to go back to the stars that merge, because this is a big thing that I like. So I will just tell a very short little story that in 2012, there was a report of a gas cloud that was about to fall into the supermassive black hole. And the media was really having a fist, and they were so excited because they say, oh, we're going to see the supermassive black hole eating something, and it's so exciting. And then they really followed this cloud. It looked like a cloud, how it goes to the supermassive black hole. But then the damn thing survived. It didn't fall. And the reason that it didn't fall, and you can think of only, you can calculate actually, what is the mass of something that goes so close to the supermassive black hole but doesn't fall in. And it should have a mass of about 2 to 3 times the mass of our sun. But this does not look like a star. It looks like a cloud. So what can look like a cloud but is not a cloud? Most likely it's a stellar remnant. At least there are lots of ideas. As I said, theoreticians come up with many ideas. We come up with the idea that it's two stars that merge, and we gave a prediction. This is where I said that we need to come with ways to disentangle. We give a prediction that we will see more of these, because it cannot be only this lucky 2 stars that actually merged and became one star, one merger remnant that is a cloud before it will look like a new star. And we predicted that, and the Galactic Center group looked more and found many of these. So that was very exciting because it seemed to be consistent with our idea. And I see another question.
I have a follow-up question.
Yeah.
Sorry.
Go ahead.
So how do we look out into space and see that it's a cloud and not a star? What's the big difference?
That's an excellent question. It's about the difference of light that it emits. So this cloud, first of all, it wasn't compact as the Galactic Center group see images as well. So it wasn't compact as a star. It was very extended, and it wasn't round. It was looked like a spaghetti type of cloud. But then in addition, it emitted something that is mostly in infrared radiation, with no traces of what we usually expect from stars. And the idea is that when 2 stars merge together, it's an extremely messy process, and they emit a lot of gas and a lot of dust. And basically, you can hide a real star inside this mess, and then you hide the light from this star. That answering your question, Denise? Awesome. And then there is another question. How do 2 black holes actually merge as opposed to 2 stars or a star and a black hole? That's an excellent question. 2 black holes, when they come together, they emit gravitational waves. And gravitational waves, it's a type of energy. As I mentioned, right, when the 2 black holes merged, they emitted their energy, a type of gravitational waves. So where did this energy come from? This energy comes from the orbit itself of the 2 black holes. So as they go around their orbit and they emit gravitational waves, their orbit shrinks closer to one another, and they emit more gravitational waves. They shrink more and come closer to one another. And then this entire business means that they become closer and closer and closer, emit more and more and more gravitational wave until they merge. However, 2 stars, when they merge, it's as I mentioned, is a messy process, and there are some tides, and some stars give a little bit more mass, and another gives a little bit and takes a little bit more, and that's a huge thing that it's actually harder to understand. The 2 black holes merge together, and then a black hole and a star gives some mass to a black hole, and the mass that goes into the black hole goes in a type of a spiral. and it becomes very, very, very hot. We call this an accretion disk. And it becomes so hot that it actually starts to emit radiation, often is an X-ray. And we in fact see lots of these black hole star type of pairs, and they are called X-ray binaries. And we observe quite a lot of these X-ray binaries. And I think I'm probably over my time.
Okay, thank you so much, Smadar. That was a wonderful talk. And now let's move on to Rory. So let me share my screen really quick. Okay, now we're going to listen to Rory, who is a grad student at UCLA. Rory has loved astronomy since he was given a solar system placemat on his second birthday. He volunteered for years at the Highland Road Park Observatory in Baton Rouge, Louisiana, and graduated from Louisiana State University before joining the UCLA Astronomy Graduate Program in 2018. He now does research in massive stars at the very center of our galaxy, which Smadar mentioned, and he works with Professor Twando and Andrea Ghez. So Rory, we look forward to it. I'm going to stop sharing so that you can go ahead and share.
Alrighty, if we're ready to just go ahead and get going, let me share my screen. Can you see this all right? Okay.
Loading. Looks good now.
Okay, sweet. So thank you for the wonderful introduction, Denise. As she just said, my name is Rory Bentley, and I'm going to tell y'all today about the lives of stars, like how you get, more specifically, some of the black holes that Smadar was talking about, and how you and basically everything in your day-to-day life is a direct result of the lives of the different kinds of stars. So when we go out in the night sky and you look up, the stars, they seem almost timeless. I mean, you ask your parents what the stars looked like when they were young, neglecting like pollution and stuff. You ask your grandparents, the sky doesn't appear to have changed for on human timescales for so like hundreds of thousands of years. However, this is just because stars take a long time to evolve. They actually have their own very complicated life cycles that they live out over kind of millions to billions of different years. And so then they go through these different cycles. There's almost like a bunch of kind of recycling that goes on in the lives of these stars. This picture, it looks a little complicated at the moment. There's a lot of different different steps, but this is just showing how essentially material goes around and is recycled in kind of generations upon generations of stars. And almost everything, all the atoms that make, the computer that you're looking at, the food that you eat, you yourself, is all a direct kind of result of this kind of cyclical evolution of stars. So from here, we're going to go through and talk about the three different ways stars live out their lives and kind of what comes out of each one. They all start the same, though. You start with a big cloud of gas out in space. If you don't know, a big cloud of gas in space is called a nebula. And most nebulae are made mostly of hydrogen. Hydrogen is the lightest and simplest and most common element in the universe. About 75% of all matter in the universe is hydrogen. And so when we look at a nebula, we see that little bits of it are kind of slightly more compact and denser than other bits. These little knots, over time, they have their own kind of gravitational pull. And so they collapse and shrink. As they shrink, they also heat up. And so these little knots are getting denser and denser and hotter and hotter. Eventually, the centers of these knots, they get so hot and dense that the hydrogen atoms in the gas, rather than kind of just skipping off of each other like they do at most temperatures and most densities, they actually stick together and fuse into a larger element. In this case, hydrogen atoms fuse to form the second lightest element, that's helium. One of the byproducts of this nuclear fusion is a little bit of light. And this light, it races out of the knot. And as it does that, it bumps into things and can actually slow down and stop material falling into the knot. So it essentially stops the collapse of our knot, our protostar, as it's called. As the knot gets denser and denser, you get more and more light, and eventually you get so much light coming out of this protostar that the collapse stops altogether, and you just end up with your star floating by itself out in space. Maybe with another star nearby if it's a binary, but that's a whole complicated other topic. So that basically, the kind of the outwards pressure of light versus the inwards pull of gravity is essentially what keeps a star ticking. It's what drives, it's the reason the stars shine and why they live their lives. It's this kind of this balance between the outwards force of pressure and the inwards pull of gravity. The outwards force of pressure is driven by this nuclear fusion that's going on in the core of the star. And so over time, the star will burn that hydrogen fuel and turn it into helium. When a star is burning hydrogen into helium, it's on what we call the main sequence. And this is the middle age of a star, and it's where the star spends most of its life. Stars are a pretty varied bunch, even main sequence stars. They come in a wide range of like brightnesses and temperatures. The sun is a pretty medium-sized star. You get the smallest stars are maybe 10 times smaller than the sun, and the biggest ones are maybe 100 times, well, when I'm saying times the size, I mean they're about 100 times more massive, or like 10 times smaller. So the sun's a pretty regular star. Kind of, we're gonna say it's a mid-sized star for this talk. Now, stars, as I said, they're burning their hydrogen into helium, but they only have a limited amount of hydrogen in the core. Eventually, it runs out of fuel. When that happens, suddenly that balance between pressure and gravity is lopsided in favor of gravity. And so gravity likes pushing things together, so the core begins to shrink and collapse. It collapses until one of two things happens. First is that is if the atoms themselves, they get so bunched up together that they just completely, kind of the repulsive force the repulsive force between the atoms just says, nah, we're not getting closer. Think like if you take two magnets and try to push them together, if they're not aligned correctly, they'll repel each other. It's a lot like that. The other case is if the force of gravity is strong enough, it can sometimes overcome that repulsive force and cause the atoms to start fusing again. This would be like a heavier atom beginning to burn rather than the lightest atom, hydrogen. So the core will collapse until one of these two things happens. For the smallest stars, once the star runs out of hydrogen fuel, it tries to collapse, but the repulsive force between the helium atoms just says, nope, we're not getting any smaller. And so the star gets effectively stuck. It can't collapse any further, but it can't burn any more fuel. So what happens then is that the outer layers of the star begin to cool down and kind of fall onto the core until it all just kind of sinks down into this husk of a star. It's just the core sitting in space, not burning anything, slowly cooling down over billions and billions of years. So this is what happens to the smallest stars. One thing to note, though, is we've never actually seen this happen. The smallest stars burn through their hydrogen fuel incredibly slowly. And the lives of these stars are, or the kind of the time that they spend burning hydrogen is longer than the age of the universe. So the universe is too young for any of these smallest stars to have actually reached the end of their lives. For bigger sized stars, we do know what goes on. So for kind of sun, mid-sized stars, the universe is old enough for these stars to have lived out full lives. What happens then is when the core contracts, it's able to start using the helium ash produced by the hydrogen burning as fuel. In this case, it starts turning it into carbon, a heavier element. As this happens, as the core contracts, it begins to actually produce much more energy. And this causes the outer layers of the star to balloon out, and the star gets much brighter. It becomes what we call a red giant star. So the sun is slated to become a red giant star later in its life, about 5 billion years down the road. You don't have to worry about any of this happening in your lifetime. When the sun becomes a red giant, as I said, it's going to balloon out. It's going to get much, much bigger. In fact, we believe it's going to get so big that it's actually going to destroy the 3 innermost planets, Mercury, Venus, and Earth. Mars, we think Mars will probably be fine, but we're not 100% sure. And so when this happens, the sun will get much bigger and much brighter. And so this really kind of sets the ultimate fate of the Earth. Eventually, though, the core, it runs out of helium fuel. It'll try and contract again, because again, that balance is broken between pressure and gravity. And it eventually collapses until what happened with the smaller stars happens. What happened with the smaller stars happens again, but with a different element this time. The sun, say, when it tries to burn carbon, the carbon atoms, they'll get too scrunched up together, and then they'll tell gravity, you know what, no, we're done collapsing. We're just going to sit right here. When this happens for a sun-like star, the outer layers actually get kind of knocked off the star and thrown out into space. And this carries a bunch of gas, and a bunch of kind of heavier elements that were produced inside the star from these fusion processes. And these fly off into space, and they produce these really pretty nebulae like the one that we see here. At the center of the nebula is the exposed core of the star. This is what we call a white dwarf. Now, a white dwarf is just the core of a star that's kind of lost the outer layers of the star. It's just now floating out in space. They're actually not very big in kind of astronomical terms. They're only about the size of the Earth. Despite this, they usually contain, say, about the same amount of material, or same amount of mass as the entire sun. So they're incredibly dense. If you were to take like a teaspoon of white dwarf material, it would weigh about as much as an elephant. And they'll also eventually, like those tinier stars, they'll just cool down over billions of years. Now, what about all that gas that was launched off into space? Well, that flies off into space and kind of just gets turned into future generations of stars. Kind of medium-sized stars produce a lot of the key elements that that make up life on the Earth. Carbon, nitrogen, and oxygen are all produced and released into space at the ends of these kind of mid-sized stars' lives. And so it's taken generations of these stars to make make us walk, make us talk, make the beautiful landscapes like you see in this picture. Now, for the largest stars, we have a even crazier end. What happens for the larger stars is they have more mass, so they can compress even more. They can burn even more, even kind of heavier elements and even heavier fuels. When this happens, they kind of balloon out to an even bigger type of star than a red giant. We call these stars red supergiants. And these are the largest types of stars that we find or that we know of. If you were to take a typical red supergiant and place it in the solar system, Earth would be way deep inside the star. You can see in this picture, it shows the orbits of the innermost 6 planets, and this red smudge marks the typical size of a red supergiant. And you can see the Earth's orbit is deep, deep within the star. So these red supergiants, they burn heavier and heavier fuels until they try to burn iron. Now, when a star tries to burn iron, it runs into a problem, because when you try and slam iron atoms together to get a heavier element and some light that fights gravity, well, trying to fuse iron doesn't actually produce that extra little bit of light. So the star runs into a problem because trying to fuse iron doesn't do anything. When this happens, that balance is between pressure and gravity is completely broken. Gravity totally wins out, and the core of the star just violently implodes on itself. Suddenly, there's nothing that can hold up, that can fight gravity at this point. The core collapses from like an object about the size of the Earth to an object maybe the size of a city. When this happens, the protons, the neutrons, and the electrons that make up the atoms all kind of fall into each other and are kind of crammed into one tiny space by gravity. The protons and the electrons they fuse together, and when they combine, they produce a neutron. So you end up with this teensy tiny ball of neutrons at the center. Eventually, the neutrons, they themselves have their limits of how much they'll be compressed, and so they will stop collapsing. When this happens, there's essentially a rebound of kind of material falling, kind of chasing the core down into the star. This rebound kind of flies out back into the material, kind of chasing the core down, and causes a huge explosion that completely destroys the rest of the star, leaving just the little core in the center, the little tiny ball of neutrons, which we call a neutron star. I sort of got ahead of myself, but here's this the slide explaining that. This huge explosion is complete chaos. Atoms are flying everywhere, crashing into each other. It's how you make some of the biggest elements. And these are also some of the brightest, and kind of a supernova, this explosion, is one of the brightest things that we see in the universe, and it's really important for a lot of astronomy. What's left behind is the neutron star and a bunch of gas just flying off into space. Neutron stars are even more extreme than white dwarfs. Now we're talking about taking an object, the mass of the sun, and not compressing it to the size of the Earth, which is maybe 10,000 miles across, but to something 10 miles across. So these are super dense objects. The gravity near the stars is actually so strong that it warps light as it goes by. So in this picture, you can see in the center you have a neutron star, and you have these weird arcs bending around the star. Those are that's starlight that's getting warped by the gravity of the neutron star itself. While like a white dwarf, a teaspoon of material is about the weight of an elephant, a pinhead of neutron star material is about the weight of a supertanker. So very, very dense. Now I've been talking about different sizes and things, sun size, the size of the Earth's orbit, but this is all, what does this mean? Like exactly what's the size difference between them? If you were to take the sun, which is about 100 times the width of the Earth, and compress it down to the size of a modest sized dog, like one of these good boys that you see here on the slide, so a little bit less than a meter, a neutron star would be about the quarter the width of a human hair, probably even less than that. So very, very, very tiny. On the other hand, a red supergiant would be larger than some of the largest skyscrapers. So much, much larger than the dog, and almost incomprehensibly larger than the neutron star. So there's a lot of variety and a lot of variation in the different types of stars in the universe. Smidar sort of alluded to this in her talk, but for the largest stars, even the force of gravity can overcome the repulsive force between the neutrons. And so the neutron star will actually keep collapsing in the supernova, in the very center of the supernova. And in that case, it becomes, it just collapses almost infinitely and becomes a black hole, like one of the kind of the stellar mass black holes that Smidar was talking about. We think that these the ends of the largest stars is actually the main way we get black holes in the universe, and like the ones that we see in LIGO. Now, the supernova actually produces a whole bunch of different types of elements and flings them off into space. Some of the elements include things like they produce a lot of iron. They produce basically all the gold that we find in the universe, and some other elements like potassium, uranium, lead, titanium, things like that. And so this actually explains kind of why a lot of the elements in the universe are, why some of them are rarer than others, because a lot of iron is produced in these supernovae, and it explains, and that's launched off into space and becomes the fairly common element that we find here on Earth. But supernovae also, even though they're one of the few producers of gold in the universe, they don't produce that much of it. And so it's relatively rare compared to like iron, like I just mentioned. So with this, I'm pretty sure I'm coming close to time, so I'm going to start wrapping up. So we're going to come back to this picture, and you can now, hopefully you'll have, you'll sort of understand this cycle more, and you can, see kind of how all these these different generations of stars have produced different elements that go on to make the stars like the sun and even the planets themselves are the direct result of kind of generations upon generations of different of stars. And with that, I'm going to wrap up. I'll take any questions, and I hope y'all enjoyed the talk and learned at least one or two things.
Thank you, Rory. I'm learning a little bit of this in my class, so that it was really interesting to see it in this format. I do have questions, okay, but we'll answer the questions that are in the chat first. I have quite a few questions.
Yeah. Okay. So, so the first question is, what happens to the planet that gets swallowed by a star? I think this is asking about the sun expanding. So, what happens is, as the sun expands, the Earth, it's kind of, it's pretty, as the sun sort of, as the Earth sort of, the sun expands, almost sort of enveloping the Earth's orbit, the Earth is going to fall into the sun. I'll try, my understanding about what happens, I'm no expert in this field, is that the Earth, it'll sort of, the sun's outer layers are very kind of, actually very misty and tenuous. So the Earth will spiral in into the deeper parts of the sun and essentially dissolve over time. It will probably actually, my understanding is that it's actually will probably take a few thousand years for the Earth to be destroyed, at least once it falls inside the sun. We won't be able to see that, but eventually it'll be destroyed. And this will be the same case with Mercury and Venus. The second question is, how did the big black hole in the center of the galaxy get made? From stars too? That is an excellent question. And my understanding is astronomers are still trying to figure that out. So the big black hole in the center of the galaxy is, we believe it's produced in through a different mechanism. And so it's through, we don't actually know quite how they got started. We have some ideas, but we think that they probably formed from some big collapsing gas cloud, like an even bigger one earlier in the universe, and just over time got built up by different things falling into it, say more gas, stars, other big black holes, things like that. But that is a really good question. Even though I gave some ideas about how we think it happens, we actually don't quite know for sure.
And I actually do have some questions.
Sure.
So this is kind of, my questions go throughout the talk. So
Sure.
my first question is, what are our limits in observation? Like, how are we able to see the small stars in comparison to like the very dense ones? Like, is there a difference in like, because you showed us kind of the drastic size differences in stars. So are we able to see them all equally, or what are our limitations in observations?
That's a really good question. So for small stars, they're quite faint. So we can, our limitations are mainly limited by we can only see the nearby ones. So we can get, if we assume we're in a pretty regular kind of area of space, we can kind of count them. Smaller stars are dimmer, so we can only see the nearby ones. Bigger stars, we can see them much further away, but they're also rarer. So like, they're like a big mountain off in the distance. You can see it from a long way, from all over the place, but they're not really, there's not a bunch of them. Does that answer your question, Denise? Okay. Got another question in the chat. Why do stars fall into certain areas of the Hertzsprung-Russell diagram? Oh, that's a really interesting question. So the Hertzsprung-Russell diagram, for anyone who's not familiar with it, it's a really important plot in understanding stars. That's just the plot of how bright a star is versus its temperature. And a lot of astronomy is built off like looking at where different types of stars fall on this graph. It's driven by a lot of complicated internal processes. There's a lot of things going on in the star, so I'm going to try not to dodge this question as much as I can. At least for main sequence stars, they fall onto the Hertzsprung-Russell diagram or different parts because they have different masses. Like smaller stars the gravity can compress it more and generate more light, or not smaller stars. They can compress it less and they don't generate as much light. And so they end up being dimmer and cooler. For larger stars, it's the opposite. They end up becoming much hotter because they have much more kind of energy input. And the reason like red giants and stuff are cooler and kind of the red stars are actually cooler than blue stars. That's because yes, they have more energy, but it also sort of causes the heat from the core causes the star's outer layers to expand. And so the energy gets and the temperature gets more sort of spread out over the star. That's probably not the most satisfactory explanation, but it's there's a lot of things that go into this, and that's a very good but also a very complicated question. And it's been taken about 100 years of astronomy to really explain all that.
I actually have another question.
Okay.
And it's not really related to what we just talked about, but are there stars being born right now that will eventually do this whole process over again? And how can we observe the stars being born?
Oh, yeah, that's a really great question. So stars of all the three different sizes that we talked about are all being born right now. Like, actually, I'm going to go back to a long slide a long ways ago and look at this picture. So this is a nebula called the Carina Nebula, just as an example. And although I don't know exactly where any are in this picture, I know there are some like baby stars that you can see like in this nebula. And we can get some estimates about how big they are, and we see both big ones and small ones. Was there a second part of your question? I think I sort of got lost. Okay.
But then I have one last question because we're out of time. So how do we know what stars are made of by looking at like using the observations of stars that we've made?
So that's a really another really interesting question. So a lot of our information about what stars are made out of is from this technique called spectroscopy, which is for those of you who don't know, spectroscopy is you take light from your star and basically break it down into its constituent colors, sort of like when you hold a prism up to light and break it into a rainbow. And then you look at how much of each color you get. Certain atoms emit and absorb light at very particular wavelengths. So we can look at like how much light is getting absorbed at some wavelength. And then that can give us some estimate about how much there is of each element. This is actually what I work on, so is spectroscopy and stuff. And that's the main technique. That good?
Yeah, great. Thank you so much. I'd like to thank both of our speakers. I had a lot of fun listening to both talks. So I really appreciate you both taking the time to speak to us.
Thanks. Anytime.
Now, I will share my screen again and we'll move on to trivia for those that are able to stay with us. Okay, and the rules of trivia are we will have 20 seconds, 30 seconds for each question, and then we'll go through the questions all over again. And at the very end, feel free to, or please email your answers to us, and potentially you'll get a prize. So we'll start now. Oh, it's not working. Well, that was trivia. I hoped you all got your answers. If you have 6 or more correct answers, please email us at outreacha@astro.ucla.edu and take a screenshot of your answers, send it in, and then we'll enter you for a raffle for some of our prizes. Thank you so much to Rory and Smadar again for telling us a little bit about what's out there and what's in us. So thank you so much. I think that's all, and I hope everyone has a great night.